B. Naresh, working as an assistant professor in AC department. And today's topic is problems on current gain of transistor configurations and current components. So in this session, we are going to discuss some of the problems on transistor configuration, that is common base, common emitter, as well as common collector configurations, as well as we need to discuss some of the problems on current components like the emitter current, the base current, as well as collector current in terms of the DC current gains. So first we'll see a transistor has the base current is 100 microamperes and the collector current is 2 milliamperes. Solve beta of the transistor and alpha of the transistor, emitter current, and if IB changes by plus 25 milliamperes and IC changes by 0.6 milliamperes, then calculate the new value of beta. So for this case, first you note on the given specifications, like they given that IB value. So IB value is given as 100 microamperes and IC value is 2 milliamperes. So based on that, we need to calculate first the beta of the transistor and alpha of the transistor. So if you want to calculate this beta is derived from the common emitter configuration. So in this case, we know that in a common emitter configuration, the DC current gain, that is represented as beta, it is defined as, it is a ratio of output current to the input current. In this case, the output current from the common emitter, the output terminal is a collector and input terminal is acts as a base. So from that, it is defined as, it is a ratio of collector current to the base current. So hence, to observe this beta is represented as IC by IB. Hence, you can substitute IC value is 2 milliamperes and this is 100 microamperes. So means you can write this is 2 into 10 to the power of minus 3 by this is 0.1 into 10 to the power of minus 3. So means 0.1 milliamperes. So this 10 power minus 3, 10 power minus 3 is a cancel, and the beta becomes to 20. Then we need to calculate alpha. So alpha I can write in terms of beta by 1 plus beta. I can substitute this value, 20 by 1 plus 20. It gives the alpha value. Similarly, in the problem, another question they asked the emitter current IE. So to calculate this emitter current IE, it is a summation of base current and collector current. So hence we have IB value is 100 microamperes and the collector current is 2 milliamperes. Then it gives that the emitter current deal. Then again in the fourth one, they are asking that if the base current is changes by 25 milliamperes and the collector current changes by 0.6 milliamperes and find the new value of beta, means we need to write. So we know that the beta is defined as IC by means output collector current to the base input current. Now we need to find out the new collector current. So that new collector current is defined as the 2 milliamperes. This is the old one, and it is increased by 0.6 milliamperes, hence it becomes 2.6 milliamperes. And IB, again we need to calculate a new base current. The old base current value is 100 microamperes. Then the new is 25 milliamperes. So means this is 0.1 milli plus 25 milli means 25.1 milliamperes. Now calculate the new DC current gain of the transistor, that is the new IC value is 2.6 milliamperes divided by new IB value is 25.1 milliamperes. Then you can use the new DC current gain of the transistor. Now, second question. Solve the base, collector and emitter currents and VCE for the common emitter circuit shown in below figure. That is VCC is the 10 volts, VBB is the 4 volts, RB is the 200 kilo ohms, RC is the 2 kilo ohms, and VB on is 0.7, beta is 200. So for this case, this is the given circuit for the common emitter configuration. Means this is the emitter is connected to ground, base is taken as the input, and the output is measured across the collector terminal. And across the collector, it allows collector current, that is IC, and the bias resistance RC is represented as 2 kilo ohms. And the base is represented as input, and it allows the base current. And here the biasing resistance is represented as 200 kilo ohms, and with the biasing voltage is 4 volts. Now here we need to find out the base current, collector current, and emitter current along with the VCE parameter. To identify this base current, means across this RB, we need to identify the base current, and internally we have this potential difference voltage between these two terminals, that is represented as VBE on. So means when this particular PN junction diode is on, it produces a cut-in voltage, that is represented as VBE on. To identify this, to absorb this base current, then apply the KVL at the input side. It starts from the VBB and this lower potential node, means V by R. The potential difference between these two nodes is represented as VBB minus VBE on by your resistance across this resistance is RB. So hence we can write. So how to write this one? So that is 4 minus VBE is a 0.7 divided by the base resistance is 200 kilos, means 200 into 10 to the power of 3. So hence it gives that 4 minus 0.7 divided by 2 milliamperes, that gives that 16.5 microamperes. So again, if you means this is 16.5 microamperes, and based on this given circuit, the circuit is actually the CE configuration. And from the CE configuration, we know that the collector current relation IC is represented as beta times of IB plus 1 plus beta times of IC naught. And where IC naught is a reverse saturation current, and that is a very, very small, hence the IC is approximately equal to beta times of IB. So from this relation, and we observe that the here, and given the problem specification, beta is defined as 200, hence so IC is equal to beta times of IB, means this is 200 into IB value, we got that 16.5 into 10 to the power of minus 6. So hence it gives that 3.3 milliamperes. And apart from that, we need to calculate emitter current, and from the transistor construction, we know that the emitter current is summation of base current and collector current. So here the base current is 16.5 microamperes and collector current is 3.3 milliamperes. Then you can add these two, it gives that the total emitter current, that is 3.3165 milliamperes. Now again, in the problem specification, we need to calculate this VCE parameter. To observe this VCE parameter, apply the KVL at the output side from this VCC node to this lower potential. So hence now I'm going to find out the KVL relation means how to write this KVL relation, that is VCC is equal to the voltage drop across this RC resistance is represented as IC times of RC plus, and internally these two nodes we have the a potential difference, it is represented as VCE. So hence that is VCC is equal to ICRC plus VC. From this relation we require this VCE parameter, that VC is equal to VCC minus IC times of the RC. So hence it is represented as VC is equal to VCC minus IC times of RC. In the problem, they given that VCC is a 10 and IC value we observed that 3.3 milliamperes and RC value is 2 kilo. Then you can substitute these values to get this VCE, that is equal to 3.4 volts. We'll see another problem. In a common base connection, the emitter current is, means here they given that IE is 6.28 milliamperes and the collector current is 6.2 milliamperes. Now we need to calculate alpha, beta and gamma. So generally we know this based on these given specifications, and under the common base configuration we are estimating the alpha. So in a common base configuration, so means what is alpha is defined as is the ratio of output current to the input current. Means in a common base, output current is represented collector current and input current is represented as emitter current. Hence, first you should identify this one. Alpha is equal to IC divided by IE, means IC is 6.2 into 10 to the power of minus 3 divided by IE is 6.28 milliamperes. They can solve, then it gives the alpha value. Then, if you want to identify this beta, so beta you should write in terms of alpha value. So means you can write beta is alpha by 1 minus alpha. Means you can substitute. We'll get alpha value here. That is means 6.2 by some 6.28. That is nearly equal to some 0.9 something. So you can substitute here. Then you can observe the beta value. After that, you can observe this gamma. Gamma is represented either 1 by 1 minus alpha, or you can choose 1 plus beta. So means either you can use this formula or you can use this formula to get this one. So already alpha we identified or beta also identified. You can substitute beta value here or you can substitute alpha value here to identify the gamma for this case. Next one is the reverse leakage current of the transistor when connected in CB configuration is 0.2 microamperes and it is 18 microamperes when the same transistor is connected in common emitter configuration. So solve alpha and beta DC current gains of the transistor. To identify this one, and we know that if you are in a CB configuration, IC, the collector current is represented as alpha times of IE plus, we can write this is ICBO. So means where this is ICBO is nothing but a reverse saturation current when the collector base junction is open circuited. Similarly, if you return this common emitter configuration, IC current is represented as beta times of IB plus 1 plus beta times of IC naught. So means you can also write this is IC is equal to beta times of IB plus, in terms of this one we are rewriting this expression in for common emitter 1 plus beta times of ICBO, means this one from this relation we know that this 1 plus beta times of ICBO is nothing but it acts as ICEO, means so this parameter entire relation belongs to a reverse saturation current when the emitter terminal is open circuited. So that is the reason. From this we can write. So when the transistor is connected in when connected CB configuration, that is 0.2, means this is 1 plus beta times of ICBO. They given that ICBO is 0.2 microamperes, and with the same transistor is connected to CE, that is reverse saturation current, that is ICO is 18 microamperes, means this is 0.2 into 10 to the power of minus 6, that is equal to 18 into 10 to the power of minus 6. So from this we know this 1 plus beta is equal to 18 into 10 to the power of minus 6 divided by 0.2 into 10 to the power of minus 6. This 10 power minus 6, 10 power minus 6 is the get cancel. Then this 1 plus beta is equal to 18 by 0.2 is nothing but 90. So hence beta is equal to 90 minus 1. Then beta value is 89. So hence we observe this beta DC, means the DC current gain of the transistor. Now by using this relation, now we need to calculate alpha. We have the one relation between alpha and the beta. So we can write this alpha in terms of beta, means beta by 1 plus beta, means beta value is 89. 89 divided by 1 plus 89, that becomes 89 by 90. It gives that the alpha value of transistor. Now the next question is, a transistor operating in CB configuration has the collector current is 2.98 milliamperes, IE is 3 milliamperes, and IC naught is 0.01 milliamperes. Solve the which current will flow in the collector circuit of this transistor when connected in common emitter configuration with a base current of 30 microamperes. Means in this case, the given specifications are the collector current is 2.98 milliamperes and the emitter current is 3 milliamperes and the reverse saturation current is 0.01 milliamperes. Now we need to find out, so from the common base configuration, we know that IC is equal to alpha times of IE plus ICBO, means the reverse saturation current. So hence from this I'm going to calculate, from this relation I'm going to calculate alpha, means IC minus IC naught by IE. So then you can substitute the given specifications, then you can observe this alpha value is 0.9. And by using this alpha value, we should write observe the beta value. We know that beta in terms of alpha, that is alpha by 1 minus alpha. So hence we can substitute this all these parameter alpha value here. Then you can observe the beta value is 99. Now we need to calculate. So the collector current for a CE configuration, we know that IC is equal to beta times of IB plus 1 plus beta times of IC naught. So beta is observed, IB already there, IB in a problem specification, IB is given as 30 microamperes, hence substitute the IB value and 1 plus beta times of IC naught. They can observe this, the collector current is 3.97 milliamperes. Now, the next question is, a certain transistor has alpha of 0.98 and the collector leakage current IC naught of 25 microamperes. Find the collector and the base currents when the emitter current is 2 milliamperes. So for this case, they given that alpha is a 0.98 and the reverse saturation current is 25 microamperes. Now we need to find out IC and IB, and for this case the emitter current is 2 milliamperes. So based on this given configurations here, we know this IC is represented as alpha times of IE plus IC naught. So this is the derived from the common base configuration. Hence, you can substitute this one. Alpha value is 0.98, IE value is 2 milliamperes plus, and the reverse saturation current is 25 microamperes. Now we can solve this one. We can observe the IC value here. So this one 0.98 into 2 into 10 to the power of minus 3 plus 25 into 10 to the power of minus 6. It gives the IC value. So this is the IC value. Now we need to calculate the base current, and we know that from the transistor construction, the emitter current is always the summation of base current and collector current. So hence, so from this we need to derive this IB. So hence IB is equal to IE minus IC. So IE is a 2 milliamperes minus, you can substitute this IC value here, then you can absorb this IB. Now, another question is, show the collector current shown below figure, given the Q point values are to be ICQ is 1 milliampere and the VCEQ is a 6 volts. Assume that VCC is a 10 volts, beta is 100, VB on is 0.7 volts. So this is the given circuit. They are given that here the VCC is a 10 volts, beta is defined as 100, and this is VB on. The VB on is 0.7 volts. Then the Q point values are defined as ICQ is 1 milliamperes and VCEQ is 6 volts. Now we need to find out the collector current, how much collector current is flows through this given circuit. For this case, so to observe this collector current, first we need to identify what is the collector resistance and base resistance as values. Then you can apply the KVL at this output side. So to write this one, so you can write this one. So it is represented as VCC is equal to, so here the Q current means Q point current ICQ times of RC plus we can write VCQ means if you apply the KVL at this output side, we can write like this: VCC is equal to ICQ times of RC plus we can write VCEQ. So in this case, now we need to identify the unknown parameter is RC. So hence I am going to find out this RC from this relation, means VCC minus VCEQ by this is ICQ. Hence I represented this one, the RC is equal to VCC minus VCEQ by ICQ. Then we can substitute the given specifications. VCC is a 10 volts, VCEQ is a 6 volts, and IC is a 1 milliampere. Then you can observe this collector resistance is 4 kilo ohms. Now, so we observe the collector current, how much means for this resistor identified. Now again, then we need to identify the base current. So we know that generally IC is represented as beta times of I. Means I'm writing this one in terms of Q point. So ICQ is equal to beta times of IBQ. Hence, from this IBQ is defined as ICQ by beta. Hence, ICQ value is 1 milliampere. Beta is given as 100. Then IB value is 10 microamperes. Then similar to that, we need to calculate this RB. To understand this, to observe this RB, apply the KVL at input side. From this, how to write this one? VCC is equal to IBQ times of RB, means then plus again the potential difference between this base node to emitter node, that is represented as VBE on. And from this, the unknown parameter is RB, hence we need to calculate this RB, that is VCC minus VB on by IBQ. So hence here I represented directly that one, VCC minus VB on by IBQ. So VCC is the 10 volts, VB on is the 0.7, IBQ we observed as 10 microamperes and 10 into 10 to the power of minus 6, it gives that 0.93 mega ohms. Now, the another question is, the transistor has the emitted current is 10 milliamperes and alpha is 0.98. Find the values of IC and IB. So based on the given specifications, they given that alpha is 0.98 and emitted current is 10 milliamperes. Now we need to calculate IC and IB. So how to find out this one? So we know one relation, IC is equal to alpha times of IE plus ICBO, where ICBO is a reverse saturation current. It's very small, so hence IC is approximately equal to alpha times of IE. So hence this IC is equal to alpha value is 0.98, IE value is 10 milliamperes, means 10 into 10 to the power of minus 3. So means this is IC value is so 9.8 milliamperes. IC is 9.8 milliamperes. Then we have this IE value and IC value. Now we need to calculate the base current. So hence we know that from the transistor, the emitter current is summation of base current and collector current. Hence, so from this we need to derive this base current. So hence IB is equal to the difference between IE and IC. So IE is 10 milliamperes, 10 into 10 to the power of minus 3, and IC is 9.8 milliamperes. So hence that is 0.2 milliamperes, that is base current. Okay, then we'll see another question. In a common base connection, the emitter current IE is 6.28 milliamperes and the collector current is 6.20 milliamperes, and find the common base DC current again. So a common base means this is alpha. Alpha is defined as it is a ratio of output current to the input current. That is, output current is collector current and the input current is emitter. So hence this is 6.2 into 10 to the power of minus 3 by 6.28 into 10 to the power of minus 3. Then it gives the alpha value. Okay. Then if a transistor has a value of alpha is 0.97, find the value of beta. If a beta is a 200, find the value of alpha. So for the first case, in a case 1, they given that alpha is a 0.97. In this case, we need to find out the beta. In a second case, they given that beta is a 200. Here we need to find out the alpha. Means we need to write these two relations. What is the relation between beta in terms of alpha and alpha in terms of beta. In the first case, then you can identify this beta in terms of alpha, that is alpha by 1 minus alpha, means that is 0.97 divided by 1 minus 0.97, it gives the beta value. Similarly, and second case, they given that beta is at 200, then we need to calculate the alpha value. So how to identify the alpha? So means we need to express this alpha in terms of beta. So hence alpha is equal to beta by 1 plus beta. So what is the beta value? Beta value is 200 and this is 1 plus 200, means 200 by 201, that gives the beta. So this gives the alpha value. Alpha is equal to 200 by 201. That ratio is the gives the alpha value. Now the next question is, a transistor has beta is 100 if the collector current is 40 milliamperes, and find the value of emitter current. So for this case, they given that beta is 100, collector current is 40 milliamperes, then find the value of emitter current. So in this case, we need to find out how much emitter current is flows here. Then you can assume this beta is 100 means in a common emitter configuration, that is IC by IB. So means their beta is 100, then so IC value is 40 milliamperes, and IB is unknown parameter here. So then you can calculate from this. So 100 into IB, that is equal to 40 into the power of minus 3. Here this IB is equal to 40 into 10 to the power of minus 3 by 100. This is the base current value. So by using this relation, we identified the base current. Now we can calculate emitter current. What is emitter current? The summation of base current and collector current. So already collector current is there, 40 milliamperes, and now we observe this base current. You can substitute these two in IC place and IB place to get this IE value. Now, for the transistor circuit having alpha is 0.98 and reverse saturation current, that is ICBO and IC0, 5 microamperes, means ICBO and IC0 is a 5 microamperes. Then IB is 100 microamperes. Now we need to calculate IC and IE, the collector current and emitter current. So for this case, and based on the given specifications, and we have the one relation in a common base configuration, IC is represented as alpha times of IE. Then so if you want to find out this one, alpha times of IE plus ICBO. But here there is no IE value, or if you have to use another relation, IC is equal to beta times of IB plus 1 plus beta times of IC0. So here IB value is 100 microamperes, IC0 is 5 microamperes. Now first we need to identify this beta. They have the alpha, so hence we should write this beta in terms of alpha. Beta means alpha by 1 minus alpha, that is 0.98 divided by 1 minus 0.98. It gives the beta value. So hence you can substitute the beta value here. So that is 0.98 by 1 minus 0.98 into IB is 100 into 10 to the power of minus 6 plus 1 plus beta, that is 0.98 by 1 minus 0.98 into IC0 is 5 into 10 to the power of minus 6. Then we can observe this IC value. So after that, now we need to calculate this IE. So hence here IB value is A and we observe this IC value. We can simply calculate IE value is equal to the summation of base current and collector current. Then just substitute these values of here, then to observe this emitter current. Okay. The next one, in a common base transistor circuit, the emitter current IE is 10 milliamperes and the collector current IC is 9.8 milliamperes, and find the value of base current. This is a simple one. So we know that the IE is equal to summation of base current and collector current. So now we need to calculate the base current. Base current means IE minus IC. So what is the IE value? 10 milliamperes. So 10 into 10 to the power of minus 3. IC value is 9.8 milliamperes. Hence that is 0.2 milliamperes. That is IB value. So the next question, the common base DC current gain of a transistor is 0.967, means in a common base mean, that is alpha value they given that 0.967, and if the emitter current is means IE is equal to 10 milliamperes. Now we need to calculate the base current. To observe this base current, first we need to find out the collector current. IC is equal to alpha times of IE. So alpha value is 0.967, IE is a 10 milliamps, means 10 into 10 to the power of minus 3. Then it gives the IC value. After this, then you can calculate the IB. So to calculate IB is equal to the difference between emitter current and collector current. So hence, substitute the emitter current here. This is 10 milliamperes minus, you can substitute this IC value here to get this IB. The next question. The transistor has the emitter current is 10 milliamperes and alpha is a 0.98. Now determine the values of IC and IB. So based on the given specifications, IE is a 10 milliamperes, alpha is a 0.98. Hence, first we need to calculate this IC. So from this, we know that IC is equal to alpha times of IE. Hence, 0.98 into 10 milliamperes, that is 9.8 milliamperes, that is IC. Now IB is equal to IE minus IC. So IE value is 10 milliamperes, 10 into 10 power minus 3 minus, this is 9.8 into 10 power minus 3, that is 0.2 milliamperes. A transistor has beta is a 150. Find the collector and the base currents if IE is 10 milliamperes. Means IE is a 10 milliamperes, beta is a 150. Now we need to find out collector current and the base current. So we know that IC is equal to beta times of IB. So from this, we know first we need to find out this beta. In that we need to find out IB. So hence beta is equal to, generally it's the ratio of output current IC by IB. So now based on this given specifications, then so in this case, first we need to find out so here otherwise you can write this IC is equal to alpha times of I based on the given specifications, but there is no alpha value, but you should convert first alpha in terms of beta. So means that is beta by 1 plus beta, means beta value is a 150 by 1 plus 150, that gives it 150 by 151. Now you can substitute this alpha value here. So means 150 by 151 into 10 milliamperes, that is IC value. So now we have this IC and IE values. Now we can calculate IB. IB is equal to IE minus your IC. You can substitute IE value and this IC value here, then to get absorb this base current. Now determine the values of IB and IE for the transistor circuit if IC is 80 milliamperes and the beta is 170. So for this case, we need to find out the base current and emitter currents here. So from the generalized expression, beta is represented as IC times of IB. So then, so to observe this one, IC or beta value they given that 170. IC they given as 80 milliamperes, 80 into 10 to the power minus 3. Then we need to calculate IB. So hence IB is equal to 80 into 10 to the power of minus 3 divided by 170. Then we'll observe this IB value. After this, you can calculate this IE. IE is equal to summation of base current and collector current. So here the base current is this one and the collector current is 80 milliamps. Substitute these two currents, then we're going to observe the emitter current. Now determine the values of IC and IB for the transistor circuit, that is IE is 12 milliamperes and the beta is 100. So for this case, now first we need to calculate IC and IB. So generally we know that IC is equal to alpha times of IE, or we know that IC is equal to beta times of IB. But here there is no IB value, so hence I use this mathematical relation. IC is equal to alpha times of IE. But first we need to define this alpha. So, but we have the beta, so hence alpha should represent in terms of beta, that is beta by 1 plus beta. So hence 100 by 1 plus beta means 101. So then IC is equal to 100 by 101 into IE value is 12 milliamperes. Then you can observe this IC value. After this, we can find out this base current by using this. The subtraction between emitter means the difference between emitter current and the collector current. Emitter current is 12 milliamperes. Substitute this ICO, then to observe the new base currents. Now the next question is, when the current of the transistor is changed by 1 milliamperes and there is a change in collector current by, when the current of a transistor is changed by 1 milliampere, there is a change in current by 0.9, and find the current gain of the transistor. Means the current of a transistor means IE. So IE value is 1 milliampere, IC value is 0.99. So based on this, we need to find out the current gain, that is, it is a ratio of means that is alpha is equal to output collector current is and input current is emitter, hence 0.99 divided by, this is milliamperes, 0.99 into 10 to the power of minus 3 by 1 into 10 to the power minus 3, that is alpha. So hence alpha is equal to 0.99. So here the DC current gain of the transistor CE is 100. Determine its DC current gain in the CB mode. So means CE mode means they given that beta is equal to 100. Now we need to find out the alpha. So means alpha is equal to beta by 1 plus beta means 100 by 101. That gives that, the ratio gives that alpha value. So up to this point in this session, we observed that problems on current gain transistor configurations and current components. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.